All right, we're back and we're going to discuss figure ground discrimination. So you see this image on the right hand side where it's either a black vase on a white background, or let the black become the background and focus in on the white that is around the black background, and you'll start to see two faces emerge, two faces that are symmetrical and um, nearly touching at the nose. What's really interesting about figure ground discrimination is that one thing is the figure and something else is the background. So you can either have the vase be the figure and the white part be the background, or you can have the faces be the figure and the vase be the background. You can hop back and forth between them pretty quickly. So you can be like vase, faces, vase, faces. But you can never have the vase and the faces truly be there at the same time. Something has to be the figure and something has to be the ground. So when we talk about it like that, we realize that, your brain is trying to figure out what is that part of the environment that I should be focusing on and what is the background that I can just ignore. So when we talk about figure ground discrimination, we're talking about the tendency to perceive parts of the field as the figure that we should be focusing on, and what parts are the ground, the part that we can just ignore. So here's another one that I thought it was kind of fun, because I think that's supposed to be the Space Needle, but it could be the Toronto Needle. I'm not sure what they were trying for. I see the Space Needle. Anyway, it's either the white part is the Space Needle and the black part is background, or you've got two black dogs nose to nose and the white is all background. So you can decide which part you want to focus on and which part you want to ignore, and you can hop back and forth. But that's the think about the world. There are all sorts of objects out in the world to see and to focus on. There are all sorts of sounds that you can focus on and let the other sounds in the world become background. That's our job with perception, is to figure out what is the important thing that I should be focusing on and what is the unimportant part that I can just ignore. What's the figure and what's the ground? Figures tend to be bigger than the other things in the field. So they catch our attention. Like bigger things tend to pull our attention as far as visual. You could also think about figures in sound, and so the analogy in sound would be louder. More symmetrical items tend to attract our attention more. Meaningful figures tend to be more meaningful than the background is. Figures tend to be surrounded by other elements in the scene. They tend to be lower in the visual field, and they tend to be more convex than concave. So I'm going to show this picture here that illustrates all those points. So the thing that it catches your attention first, and that you tend to look at first, will be the bigger thing, which probably is going to be the closer sheep. The more symmetrical thing, well, the thing with four legs is probably more interesting to you than, the background promontories that are sort of encroaching in asymmetrical ways onto the water. The meaningful thing, that's a sheep, as opposed to, I struggle to even know what I should call those, hills, promontories. I don't know what you call those things that are going into the water, surrounded by other elements in the scene. The sheep has rocks and grass and, things around it. Other items such as the promontories are not quite as surrounded. The things that are lower in the visual field, right? That oftentimes implies that it's closer to us. And so we tend to be attracted to the things that are lower in the visual field. And so the sheep is more interesting. And then convex, meaning that it's kind of coming towards us as opposed to receding from us. Now, the thing about figure ground discrimination is that really the global overall sense does take precedence over elements. The whole is greater than the sum of its parts. And so being able to look at this picture and get a whole feeling, like, I don't know about you guys, but my guess is it looks like it's in Scotland. I don't know. I find these pictures on the internet and I just grab things and I don't even check to see where they came from. I don't get permission. I just stick them in my slides. It looks to me like, sheep in Scotland. And so this overall scene for me has like this, the figure is this meaning that I have that I have sort of imposed on it. And that's what is really important about figure ground discrimination and even grouping principles. The Gestalt psychologists said that the whole is greater than the sum of its parts. So being able to process this image as a whole gives you more meaning, more significance than if you were to try and break down all the different little elements and analyze each of them separately. Once you try and take all those little elements and put them back together, you lose something. Overall, I don't want to walk away with the impression that if you were to see this picture, the only thing you would look at is the sheep. What I'm saying is that it would probably catch your attention first, and then you probably would get this global perception of this whole scene. Here's another figure ground one that I found that I thought was kind of fun, because in black lettering you see the word ground, and then inside of that, in the yellow that's inside of those letters, you actually see the word figure. So that's kind of cool. So I just thought I'd throw that in. And then also notice that the word ground is bigger. And so one of the things that you may have experienced is that you saw the word ground first, because bigger tends to catch our attention first. I'm going to go back real quick. There we go to this one with the dogs. The dogs are bigger than the Space Needle. And so I noticed the dogs first in that picture. And I also noticed the vase first. And so you might say, well, but those are the black items. Well, it doesn't have to be black. Probably bigger is the more important thing as far as what attracts your attention first. So let's talk a little bit about global precedence, and let's use the Ebbinghaus illusion as an example of global precedence. Okay. So on the left-hand panel, you see a smaller, darker blue circle surrounded by bigger light blue circles. And on the right panel, you see a bigger dark blue circle surrounded by smaller light brown circles. Or do you? You know I did this myself because I have that jerky little motion pattern and I couldn't figure out how to get that out of there. The center circle is exactly the same size in both pictures, in both parts of the panel. The center circle is the same size. Global precedence causes us to see the one on the left as smaller because it's smaller relative to the circles around it. And we see the one on the right bigger because it's bigger relative to the circles around it. So this overall pattern takes precedence over the different little elements. It's hard to convince us that those two circles are in fact the same size. Even as I'm showing you over and over again. I don't know about you guys. I'm super skeptical when people show me things. I'm like, yeah, but I mean, you could be obscuring something on one of them and not the other. And I make up little excuses for why I'm still right. But trust me when I tell you, I designed this slide and the circle is in fact the same size. It's in the same position on the blue circles. The one on the left only looks smaller because of its context, right? Because of your brain processes it in its totality. All right, let's talk a little bit about depth perception. I'm kind of glossing on a lot of these things because this isn't a class that's entirely, devoted to perception. So if you were really super interested in this, a perception class is really fun. So with depth perception, there are what we call binocular cues that rely on you having two eyes in order for you to be able to detect this kind of depth. And in fact, it's not just having two eyes, but it's having two eyes that are pointed roughly in the same direction, right? So predators like humans and owls and lions and so on all have eyes that are in the front of their heads. They're, of course, a little bit apart because we have noses or beaks in between them. So that the two eyes don't see the exact same image, but pretty darn close because our eyes are in the front of our head, as opposed to prey animals that have their eyes more on the sides of their head so they can get a wider field of vision on their sides so that it's harder to sneak up on them. The problem with them is that they don't get very good depth perception binocular cues because there's no overlap in their vision. So in the right-hand panel here, this image, we're seeing the left and the right eyeballs, and they're both looking at that cube that's in front of them. And in the left-hand lower part, we see what that cube looks like to the left eye, And in the right hand lower part, we see what that cube looks like to the right eye. So the two eyes are seeing different images. But what I wanted to talk about first is that those eyeballs have to rotate towards each other when the object is closer to the face. And those eyeballs can be straighter in their sockets when the object is farther away. This is what we call convergence. It's a muscular clue to depth because there are these muscles that rotate your eyeballs, and they send a message up to your brain to indicate how much the eyeballs are rotating towards each other and how much they're staying straight in the socket. So if there's a lot of muscle message being sent up, my eyes are rotating towards each other, my brain is going to say that object must be close to your face. If the message is my eyes are pretty much straight in the socket, the brain's going to say it must be pretty far away because you're able to have your eyes in straight in the socket. And you can test this. I'm sure you've done this. I know I have spent many a bored day in a classroom when I was growing up, and I would sit there with my my finger in front of my face and bring it closer and farther away and closer and farther away and feel my eyes rotating in and out and in and out. So I'm sure you've done little experiments like that yourself and can attest that sometimes your eyes have to turn towards each other to look at something when it's close to your face, and they can be straighter when it's farther away. The other cue, the other binocular cue, is what's called retinal disparity. That's what's depicted with those cubes in the top panel. The fact that your left eye is seeing one version of the cube and your right eye is seeing another version of the cube is what we call retinal disparity. That means that what is landing on your retina is different for your left eye versus your right eye. Disparity is referring to a mismatch. So if there is a lot of retinal disparity, that is, the eyeballs are seeing vastly different things, your brain is going to assume that the object must be close to your face because your eyes are seeing significantly different versions of the same object. If instead the object looks virtually identical to both eyes, your brain's going to say it must be pretty far away because both eyes are seeing it exactly the same way. So greater retinal disparity is associated with things being closer to your face. Greater convergence is associated with things being closer to your face. So these binocular cues are really handy for detecting the distance of an object that's probably within 6 or 8 feet of your face. Like you can definitely, using these clues together, your eyes are rotating a lot and there's a lot of retinal disparity, your brain can really get a good judgment of how far that object must be away from you. And it works for probably 6 to 8 feet. Once it starts getting out past 8 feet, your eyes are probably pretty straight in the socket. You don't have much convergence going on, and the retinal disparity is probably minimized. And so binocular cues are best for reasonably close distances. You get out past about 10 or 12 feet, these cues are going to be basically non-existent. So luckily we have other cues that we can rely on called monocular cues. And these are the ones that you probably learned about in art class if you ever took one. Here we have a nice picture of a lonesome highway heading towards a mountain range. And there are all sorts of monocular cues here. Look at the dots in the center, or the lines in the center of the road. See how big they are at the closest one, and then see how they seem to get smaller as they go off into the distance. That's what we call relative size. And it's true for all the objects in the picture. The things that are closer to us look bigger. The things that are farther away look smaller. Texture gradient. You can see more detail in the things that are closer to you. You can see some of the asphalt, the little individual rocks and stuff in the close-up. And it just becomes basically a smooth road off in the distance. Same thing for the grasses and stuff like that. Texture gradient. Relative height. Things that are closer to us tend to be lower in the visual field. Things that are farther away tend to be higher in the visual field. And so the road looks lower because it's closer to us. Even though it's a completely flat road, As it goes off into the distance, it seems to rise up. And definitely the mountains look high compared to other things in the field. But I mean, look at the telephone poles. The ones that are farther away seem higher in the visual field. That's relative height. Relative brightness. It seems like there's more sun almost on the road that's closer up to us, and then it seems a little less bright, less, I won't say shadowy, but it looks less bright off in the distance. Linear perspective, those parallel lines that make up the road seem to be coming together in the distance, right? That's linear perspective. Parallel lines seem to come together. I talked about that in an earlier piece in the same chapter, talking about, your ceiling and your floor. Linear perspective applies to all parallel lines. So every clue in this picture indicates that the bottom rectangle that I just superimposed onto the picture is closer to us than the top rectangle, right? That bottom rectangle is lower in the visual field, so that it must be closer. It's right there in the same part of the picture where you can see more detail on the road. You can see, more illumination in the lower part where the lower rectangle is. Not the lower rectangle, because it's just those two are identical to each other, but everything around it is brighter. So it makes you think, well, it must be in the part of the road that's closer to us, and the other rectangle is in the part of the road that's farther away. So when you look at the rectangle at the bottom, it seems a lot smaller than the one at the top, because for one thing, the rectangle at the bottom is filling up a lot less of that road than the one at the top is doing, right? Like the one at the top is occupying the entire road practically, and the one at the bottom is barely covering one of the center lines. So everything here is telling us that the bottom rectangle is closer to us and smaller than the rectangle at the top. Now here's one of my famous movement things. And what you see when I move it together, it forms an equal sign, because in fact, those two are identical. In fact, I made one, and then I copied and pasted it, and then I just did the animation to bring them closer together. They are in fact the same. And it looks like as it moves, it's like growing in size as it's moving, right? And that's because these monocular cues are super powerful. Our brain relies on monocular cues to help us to determine distance for anything that's more than like 12 feet away from us. And so we look for all of these signs of what's closer and what's farther away. So super important skill set that we have is these monocular cues. And then of course, like I said, if you've ever done any kind of art or anything, you know how to implement these monocular cues to give the sense of depth in a two-dimensional picture. All right, this is a great time to take a break before we shift gears into multisensory interaction and integration. So I will see you in the next segment.